So we have James Sutton, who is from IBM Hersley, and he's going to be talking to us about the Mayflower autonomous ship. So this is the emerging technology stream. So this one specifically isn't a mainframe talk, but is just about a very cool technology that can hopefully inspire you and give you some great new ideas. Sorry, should admit new people as they join. Okay. So please do ask questions in the chat as you go along if you think of any questions, and I'll be monitoring that, and I'll ask the questions to James either as we go along if they're about what he's talking about, or I'll hold them back until the end and ask them at the end. So with that, over to you, James.
Cool. Thanks, Sophie. So it's a pleasure to talk to you all today. I'm part of the Emerging Technology Group down in IBM Hersley, which is near Winchester. We're part of the wider IBM research group, but we mostly work on helping customers build new solutions to problems that they might have that don't have an easy off-the-shelf product right now to do that for them. So mostly this means we reach into the great work that our colleagues in the research do, and we pull that out and build proof of concepts and bespoke solutions for them. I'm also an architect on the IBM Wimbledon project, where we deliver a lot of our new cutting edge IoT, AI and sports work. But unfortunately, as you may know, Wimbledon didn't quite happen this year, which was actually how I ended up working on the Mayflower project, which I'm going to talk to you about today. And that's about how we have an autonomous ship and how all about the science that we're doing on it this year. So the Mayflower was originally built around the start of the 17th century. It was about 30 meters long, weighed 180 tons. It was wind powered by sails, and it could sail at about up to 5 knots, so quite slow. It carried 30 crew and 102 passengers. It set sail on the 16th of September 1620, which was about 400 years ago to this year. And this is the voyage that it's really known for. And this is the voyage from Plymouth in the UK to Plymouth, Massachusetts, carrying some of the first settlers from Europe to the New World. It took about 8 weeks to do so, and unfortunately not all of the passengers made it, but it's really well known for being, the first settlers to go to the US. So 400 years later, we have the Mayflower autonomous ship. It looks significantly different from the original. And it was built to commemorate this 400th anniversary of the original Mayflower voyage by an organization called Promare, who are a marine research organization. It was also built in partnership with an organization called MSUBS, IBM, and Marine AI. And we've all worked together with a number of other really great partners and research organizations, as well as a few universities around the UK, to build this ship. It's a 15-meter long aluminium hulled trimaran. So it's got one big piece in the middle and 2 floats either side. Weighs only 5 tons, so just 3% of the weight of the original Mayflower. And no sails on this one either. It's powered by solar panels and biodiesel. And it can travel at up to 10 knots, so quite a bit faster as well. As the name might suggest, as I'm sure you're already aware, there are no crew on board, too small for a crew. Instead, it has an AI captain, which is going to be piloting it across the Atlantic later next year. It has 2 main missions, though. The first one is pioneering autonomous technology. There's a few autonomous boats and ships out there at the moment. They're all in experimental phases, and everyone's really trying to work out how you can get a ship to sail itself autonomously across the ocean. And so this is an attempt to sort of try out some new technologies for that. The other and probably more important mission for us, though, is to gather data and conduct science at sea about the ocean. Ocean science is really important at the moment, and in fact it's the UN's Decade of Ocean Science, which starts in early 2021 and will continue for a whole 10 years. So this is a really great time to be launching an autonomous research vessel. We know very little about our oceans. 95% of them are completely unexplored. And for those 5% that we do have a fairly good understanding of, the actual chemistry of the ocean itself is still quite hard to understand. And really, we want to look at the impact that our climate change is having on the ocean, and also direct pollution on the ocean. So we've packed this relatively small ship with a lot of science, and there's quite a few research experiments that are on board it, and they're going to help us learn a lot about how the ocean works, and also give us the experience and the knowledge we need to build newer and better research vessels in the future. It's not just going to end with the Mayflower. We're going to continue and build better and more interesting ships that can do far greater ranges of science over the next couple of years. So, as I mentioned, we're going to be doing a journey across the Atlantic. The photo on the previous slide was actually from our naming ceremony in September this year, which was the 400th anniversary of the Mayflower's original journey. We were planning on doing our voyage then, but due to COVID, we've had to push things back a little bit. So instead, we're going to be sailing from Plymouth, England to Plymouth, Massachusetts on the 19th of April, 2021. And this is going to commemorate the original sailing. Once we then arrive in the US, we'll actually then sort of double back on ourselves and we'll recreate some of the Challenger expedition, because that's almost the 150th anniversary of that actual journey. So we'll be going down through the Azores and getting a very different set of data to where we'll currently be going along the North Atlantic. We didn't want to try and make our way across the Atlantic in the winter, so that's why we're going in April. The winter storms and such would be far too dangerous for such a tiny ship. So we're making the most of the time we've got between now and April to conduct a lot of sea trials. So that's going to start off with us getting the ship in the water, making sure it works on remote control, and then slowly handing over to the AI captain as we become more and more confident in it. And then eventually we'll start doing trials with the experiments, capturing data around the United Kingdom and in the Channel, before eventually we'll start doing some small journeys to potentially Dublin port and Rotterdam port. Going to Rotterdam is going to be quite exciting because Rotterdam is the first autonomously controlled port in the world. So having one of the first autonomous ships going to one of the first autonomous ports will be quite exciting. Maybe we can even get the ship communicating directly with the autonomous port controller without any human interaction, but that could be a little bit away from us right now. So here's a quick 3D model of what the Mayflower looks like if you cut it in half. As you can see, there's absolutely no space for a crew at all, and that's a very purposeful design decision. When you design a ship for science or for almost any purpose, the crew are almost always at the heart of that purpose, maybe with the exception of, say, oil tankers and cargo ships. In order to maintain a crew on a ship, you've got to have space for them to sleep in their cabins. You've got to have galleys, toilets, leisure and recreation space for them to exercise. And then you need vast amounts of storage for all of their food, fresh water. You're then also looking at increased energy consumption. You've got to power everything they need, keep them warm, keep them cool, and also make sure their food is cooked, as well as water processing and many other aspects of messy human lives. Because of this, the ships have to be big. You have to have lots of space, and you don't end up with a very efficient design. It costs a huge amount of money to build these ships, which makes it a bit difficult to optimize for doing science, because a lot of science experiments can be automated. If you think about it, you need a sensor and a computer and maybe some communications equipment, and that's all you need. You don't necessarily need people in the mix. Another important natural feature is a lot of research vessels tend to be at sea for long periods of time, and the mental health of the crews is always really important to keep in mind. Actually, a huge amount of work goes into keeping the crew happy whilst they're out at sea. If you don't have a crew, you don't have to worry about that either. So really, if you strip away the crew and you just think about what you need to do your science, you end up with a much smaller design. So in this case, all you need is power, propulsion, the compute power to get us from A to B and to do the science experiments, communications, and then the science itself. And that all fits into this really tiny ship. So it's about 15 meters long, as I said, and we actually have a 3 meter by 1 meter by 1 meter pod in the middle. It's the void right in the middle of the ship that you can see. And that's where we're going to be able to stick all of our science experiments. Some of these will be developed by other universities, but the one that we'll talk about today is done by myself and my team in IBM. Obviously, with reduced energy requirements, you can change how it's powered as well. So rather than vast quantities of diesel, we're going to be covering the Mayflower with solar panels, but we will have some biodiesel backup as well, just in case we need it. So the ship will actually be optimizing its route along the ocean to try and get as much sun as possible so that it can charge up its batteries for the traveling at night. So I'll talk quickly about how our AI captain works, because it is quite interesting. As opposed to some other systems, we're using a blend of artificial intelligence and rules-based systems. And this is a really potent mix because it gives you the ability to have all of the benefits of AI. So you can train on images and things like that. But then you can also have a really transparent and explainable rule system. So you know exactly how the ship is going to behave based on its inputs. And that's really important, especially when you're at sea, because the one thing you always want to avoid when you're at sea is a collision, and you want to know exactly how you get to make the decisions to change your course and speed. And a rules-based system does that really well. So as you can see on the left, we've got our input. So we've got a series of cameras, and those cameras are trained on thousands upon thousands of images of sea-based material. So all kinds of different types of ships from many different angles, buoys, debris, even icebergs and things like that. And it's actually a really interesting machine learning problem for image recognition as well, because you have to account for the fact that both the camera and the target may be moving simultaneously. And not only that, but the camera might not be pointing directly at the target all the time. If you think about it, the Mayflower is going to be on the ocean and it's going to be bobbing up and down in fairly high seas. So the camera is going to be moving about all over the place. And you need to be able to say, well, that's a ship over there. And in the next frame, you need to understand that it's the same ship as before. You're not just looking at 2 or 3 different ships. It's the same ship and you're tracking it across space. So that's sort of a fairly large part of our AI solution. We're also taking in radar. We have a local weather station that's stuck on top of the Mayflower, and also AIS, which is our a way of tracking boats and ships at sea. All of that data is pushed into a structured format so that we can understand it. And then we push it into our operational decision manager. This is an IBM product that's basically a rules-based system. And we've given this system all of the rules of the road for the sea. They're actually called the collision regs or COLREGS. And it's a bit like the highway code. It says, you know, if you're about to come up to another ship, should you pass them on the port or starboard side? And it defines how you should act around other vehicles in the sea. We then have another phase, which is actually trying to optimize how we're going to then route our way around in the sea. And this is looking at more about, well, moving around one ship is fine, but what if there's 5 or 6 ships in the sea in front of you? How do you get around those? And that's a lot more nuanced, and it's a bit harder to do with a simple rules system. So we've got some more optimization that goes on top of that. But the outcome at the end is that you have a heading and a speed. And that's then pushed to the control mechanisms in the Mayflower, so the propeller and the rudder. We also take a sort of a split feed of all of that data and we push it over a satellite link to the IBM cloud. This is because we want to have a digital twin of the Mayflower always running so that we can see exactly what's happening on the Mayflower at any one time, and we can understand maybe why it's making certain decisions in case we need to, in a future version, make changes to the rules or the AI. And this is really useful because it just helps us understand what's happening on the ship at any one time. And as I really want to emphasize, this is completely autonomous. There's no remote control in this whatsoever. Once we push it off on the 19th of April next year, it's going to be on its way on its own. We'll just have to hope it gets to the other side. So another way of looking at this potentially is thinking of it a bit like the Maslow pyramid of needs. If you've ever done a psychology course, you may have come across this. It's basically a pyramid of needs which starts at physiological at the bottom. So for humans, that's eating, sleeping, shelter. And at the very top, it's, are you happy with your life? So that translates quite well to the Mayflower. At the bottom, we have the core functionality of the ship. Have we got power? Do we know what we're doing? Can we avoid collisions? which is always the most important thing. The second most important thing for us is facing into the waves. We are a very tiny ship, so if a wave were to hit us from the side on, that potentially increases the risk of us flipping over, which wouldn't be very good. So we always want to be heading into the waves so that we just go over the top. Understanding the local situation around us, we're talking very, very local at this point, but assuming that we can achieve those few things, then we're okay for the next sort of level, which is our environment around us. And that's saying, right, we're okay, but what can we see around us? You know, if we look on our radar, what's a mile away from us? If we look on our cameras, is that an iceberg or a fishing boat off in the distance? Not so much understanding, you know, do we need to avoid a collision imminently, but knowing where is everything around me and how am I going to navigate around this environment? And one of the sort of the important aspects of this is just respecting the rules at sea. We want to be a good citizen in the ocean. We want to make sure that the Mayflower respects the rules and works well with other ships who are maybe hoping that we're going to be predictable in our behavior. And then we finally reach sort of the pinnacle of our pyramid, which is our core mission. And that's basically saying we want to get from A to B. We want to get from Plymouth in the UK to Plymouth in the US. We want to navigate there. We want to collect as much data as we can, and we want to execute the science experiments. So a scenario where we might have to maybe deprioritize some of these things could be where we've had a couple of stormy days at sea and we've not had enough sunlight. The solar panels are a bit drained, or the batteries are a bit drained, and we don't have enough power. We have to turn something off. We know we've got to keep the motor going. We know we've got to keep the AI captain on. So at that point, the Mayflower can actually go to the science experiments and say, really sorry, do you mind turning off now? We'll turn you on when we've got more power. And the science experiments will shut down in sort of a priority order until there's enough power to maintain the core ship functions. So quite important, but it's easy to understand, hopefully. When it comes to the rules we're following, I mentioned these COLREGS. They're actually, the proper name for those is the International Regulations for Preventing Collisions at Sea, which is, as I mentioned, is the highway code of the ocean. It's, you can see in the bottom picture, it's basically saying, how do you pass and interact with other vessels that are around you, which is really important. And we're taking all of our environmental data, passing it into that rules-based system, and it will then sort of give us a course and a heading, or maybe an option of course and headings that it would like us to take to be a safe ship in the sea. We also then, as I mentioned, we optimize that data and we use something called SOLAS for that. SOLAS is safety of life at sea. And the name's a bit confusing. It's actually more of a list of things that an experienced or wise captain would do. So a lot more nuanced than simply how to pass a ship at sea. I guess a good way to think about it is, we all know that you should indicate on your car when you go around a corner, or that you should follow the speed limit. But as we also know, sometimes other drivers on the road aren't as safe as you and don't indicate or speed or overtake you unsafely. Now, in those situations, you need to have some gut instinct, some experience to know what to do in those situations. Maybe you slow down or back off a little bit. Maybe you give them more room. And that's really what SOLAS is about. It's saying, you know, let's say someone isn't following all of the rules, or you're in a situation where, you know how to pass one ship, but what happens when there's 10 in front of you and they're all trying to crisscross in different ways? I can imagine crossing the English Channel would be quite a challenge. And that's where this really comes in. It's saying, how do you safely navigate your way around the ocean? So always the outcome we get from this is a target speed and a heading, and the overall policy that we always have to follow no matter what is do not hit anything. And that's roughly where the AI captain sort of manages the entire ship. So we'll take a bit of a turn now, and we'll talk about the science that's on the Mayflower. We've got a lot of experiments that are being developed for it. Some of them are by ourselves in IBM Research, some of them from a number of universities. So we've got Plymouth University, Newcastle and Birmingham who are working on this. And they range in sort of their the style of science we're doing. So some of them are just simply data collection. We've got a load of sensors that are on board the Mayflower, and some of them are just storing data onto hard drives, and they will be analysed once we get the ship back to land. But other experiments we're doing are looking at actually trying to do science at the edge. And what that means is, rather than just recording the data and then someone going through it back in a lab on land, you actually try to pre-process as much of the data as you can on the edge. If you can imagine, there might be a scenario where you end up gathering vast quantities of data, and it's too much to store on a hard drive, and it's too much to send back over the internet. But what you actually want is maybe one or two values out of that data. If you can do all of that calculation on the edge, then you can have a relatively decent satellite link, just send those few bits of information back to you, and you've not had to pay very much at all for it. So that's what some of these are going to be for. So whale populations, ocean chemistry, tides, and wave energy, those are ones that we're doing, which I'll explain a bit more in a minute. Music synthesis is quite an interesting one. It's more of an art project than anything, and that's where we're going to take all of the sensor data that's being captured live on the Mayflower, and we're actually going to make parametric music from it. So taking all of that audio, all of those sensors and all of the information coming from it, we'll actually try and create a song from it. I think the goal is to have a sort of 14-day-long sea shanty, which the Mayflower will be constantly generating, which could be quite interesting. How good it sounds or not, we'll have to see, but that will be a nice thing to come out of this. Microplastics and phytoplankton productivity, these are actually hugely valuable projects we're doing, and there isn't a way to do the analysis on seawater to identify the quantity of microplastics or phytoplankton in such a small space yet. So in order to do that, we have a small bottling plant which is built into the Mayflower, and it's going to be taking samples of water every couple of miles and bottling them up, and then once we get to land, it will all be shipped off and analysed in a lab. But we'll know exactly which bottle was taken where, so we can monitor the density of microplastics throughout the ocean as we're passing across it. And phytoplankton is hugely important. It's something that affects all kinds of ocean chemistry and actually is crucial to our biology and climate. A serious change to phytoplankton would have huge impacts on biodiversity, fisheries, and then eventually even the human food supply. So being able to monitor that is going to be really valuable. And then finally, temperature, salinity, and depth. These are some of the, I guess, the more standard, simple sensors that we've got on board. And it's just showing off how actually you can just have these sensors mounted to almost any ship, and they could be capturing data for you. So you could almost democratize science if you could put these kinds of sensors on ships that are already going to be traveling across the ocean. Why not stick them on and capture important information? So I'll talk about 4 of these specific experiments that we're running. And these are being run by what's called the IBM Remote Science Pod. And this is the bit that I've been most involved in over the past couple of months. And it's a rugged, reliable, and flexible edge science platform that can work for any science experiment we throw at it, whilst also being really easy to design and build for. And I'll explain that in a little bit. Here we go. So the first experiment we're looking at is about whale populations. So there's a particular species of whale called right whales, and they live in the Atlantic and the Pacific, but in the North Atlantic they are extremely endangered. They were sadly targeted very heavily by whalers over the past 100 years or so, a couple of 100 years. And in 2017, the best guess for the population of right whales in the North Atlantic, the highest number was about 411, which is really, really low. So it's really important that we're able to identify and track these whales in the ocean, which can typically be quite hard to do. They're living animals. They don't go where you necessarily expect them to go. And it can be quite hard for a human crew to try and track them down because you're chasing whales across the ocean. It's not easy. So what we're looking at doing is building a system that can automatically identify whale song or whale vocalizations. And this is really interesting because a fascinating fact about whales actually is that depending on the species, their choruses or verses, or even just the distinct clicks and pops that they make, can be distinct to the pod of whales that they're in. So they're sort of their family group. And this means that if you can identify a particular whale song or particular vocalizations, there's a chance that if you've heard it before, you might be able to identify which pod of whales that was. So you could actually track a specific pod of whales across in their migratory patterns, or in maybe the amount of whales that are in the pod, to track their population. So that's kind of where we're going with this project, which we're aiming to do. So in order to achieve this, we've attached a hydrophone transducer to the underside of the Mayflower. It's about yay long, and we've got it shielded and underneath the Mayflower. And that's plugged into a digital signals processor, which is the image you can see on the top of the slide there. And that takes the analog signal from the transducer and turns it into a digital pattern that we can actually analyze. So we're taking that audio pattern, it's about 384 kilohertz, which is a massive, massive chunk of spectrum. And we're doing that for a very important reason. Whilst we're looking at whales, which tend to be in sort of the lower frequency ranges, we're recording all of this to disk. So in the future, if someone actually says, I wonder whether you came across any porpoises or dolphins in your journey, we can hand over the data and they can have a look through it, and it'll all be there, hopefully. But we're specifically looking for whale vocalization. So we're training a machine learning model on what whales sound like, on samples of whale song, their pops and clicks. And the idea will be that we can identify these events in this live audio stream. Our sort of secret side goal, personally, be tweeting out the audio that we capture as soon as we capture it, because I think that's going to be really cool if we can say, yeah, we've just heard some right whales, and we won't say exactly where they were because they're endangered, but we'll say that we could actually let people listen to them within maybe minutes or hours, which would be really quite special. Our next experiment, so this is all ocean chemistry, and this is using an already existing IBM research technology called hypertaste. And hypertaste is a digital tongue which can fingerprint liquids that pass through it. So in much the same way that our own tongues don't have a chocolate receptor or an orange juice receptor, they're more of a generalized sensor that can take different sensations and pass them to your brain, which can then identify what tastes you're tasting. Hypertaste is the same. It's a series of electrodes, and it passes a very low voltage through the liquid and then picks up the readings. It then takes all of those readings and passes them to a machine learning model that's been trained on what a specific liquid's fingerprint or concentration looks like. So we're repurposing this technology, and we've got a really fantastic pumping system that's in development in our Norway lab that's got an array of these sensors, and is going to be sucking up seawater and pushing it through them. They're going to be sampling it, and then what they're looking for is specific minerals and compounds that affect ocean acidification. And that's an event that's happening all over our oceans as a result of the uptake of carbon dioxide in our atmosphere. You've probably heard of damage to the Great Barrier Reef, among other things, and that's really a result of ocean acidification. So the reefs, the fish that live inside them, and many other aspects of ocean biology, and that's all we're trying to identify and trace. This is all being managed again by a Raspberry Pi in our cluster, which will receive the hypertaste data, as well as orchestrating all the pumping apparatus. So deciding when it wants to take the next sample and managing the cleaning and flushing of liquids for all of those readings. We then have our open ocean wave energy experiment, which is sort of affects us a bit closer to home, but is just as important out in the ocean as well. If any of us live around the coast, you're probably aware of the effects of tidal erosion or wave erosion. And it's a big problem for a lot of people, whether you've got natural environments being eroded by waves, or if you've got man-made structures that's trying to withstand the energy of the sea. Really planning for that energy is hugely valuable when building new structures. So what we're going to try and do is using an inertial measurement unit, which is in the picture in the top there, which is basically a really, really accurate accelerometer, a bit like the ones that you have in your mobile phone, but they can take many, many more samples a second and a far, far greater accuracy. And we've got that, and that's smack bang in the middle of the Mayflower. And we're then going to use some of our HD video cameras that are on board the Mayflower to record the waves around us. So if you imagine the Mayflower is going to be trying to sail into a wave, and we see a wave coming up ahead of us, and then a couple of seconds later, the inertial measurement unit will effectively feel the Mayflower rise up and then drop down again. And we can take the information from that and basically calculate how much energy that wave had in it we know how fast and how high we moved, and we also know how much mass the Mayflower has. So we can work out how much energy was required to move us and how much was in the wave. And then we can use all of that data to train a machine learning model just from the video of the waves themselves. So just from pointing a camera at the ocean, you could actually work out how much energy those waves have in them. This is then hugely valuable, because if you imagine you're about to maybe plan a wave energy plant around the coast of Wales or something, or planning to put in some offshore wind farms, you want to know the kind of energy that those structures are going to have to withstand or even absorb. And so you could do that just by recording the waves and working out how much energy they have within them. So this is all going to be recorded onto disk, and we're going to pass it off to some of our colleagues at Newcastle University once the voyage is over, who work on training that model. So we then have a slightly similar one, which is again looking at sea level and tides and things. This is open ocean tides. So it might seem a bit counterproductive, but the Earth's ocean is not exactly smooth. Obviously it moves with the tides, but there's also a number of other factors that exert pressure on the ocean and change actually how it sort of undulates around the Earth. And that's based on the different gravitational pulls that the Earth actually has. So at any one point on the Earth, gravity is ever so slightly different depending on the thickness of the mantle. And on Earth, on ground, that doesn't really have too much of a difference for us. It's negligible. But in the ocean, when you've got vast quantities of water that are all being pulled or pushed, or always pulled slightly differently, that can have some huge effects. You actually find that over large areas of the ocean, they may be at higher or lower heights than other parts of the ocean. And it's quite important to be able to measure all of this, and it's been very difficult up until now. So our plan is to use some very accurate GNSS receivers, which are basically GPS receivers that are very accurate. They can also listen to multiple GPS constellations or satellite constellations, so GPS, Galileo, Baidu, among others. And that gives us a really accurate position on the Earth. So having dual GNSS receivers also gives us the angle of the Mayflower as well, because we'll have them in slightly different positions. And we'll be able to, over very vast distances, use our altitude to work out what the height of the ocean was at that particular point in time and space. This is obviously made a bit more difficult by tides, but that's why time is really important, because we can tell when we would be expecting a high tide in places as well. And of course, it'll take us 14 days to travel across the ocean. So we'll hopefully gather lots of data about this. And again, we've got these GNSS receivers plugged into our cluster, and we're streaming all of that data onto a hard drive, which will then allow us to analyze it and build our models later. So those are some fairly high level overviews of our science experiments. And I'll show you now what all of this looks like under the hood. You'll have to forgive me, it does look a little bit like a bomb. I am very grateful that I don't have to take this through airport security anytime. But it's a prototype. This is our first version, and we're going to be making some much more ruggedized and better versions of this in the future, hopefully. But what you can see in front of you is we've got 4 Raspberry Pi 4Bs, so relatively low power but fairly punchy little computers that are on the left-hand side there. And they've got access to 3 4-terabyte SSDs. So we've got plenty of hard drive space to store all of our data, and no moving parts as well. So if we get an unwelcome bump, nothing gets lost. They've got a network switch built in to give them network, as well as power and UPS. So as well as having the batteries on the Mayflower, we also have our own UPS, because we understand that the Mayflower may say to us, hey, I need to turn you off. You've got 30 minutes, which is great. We can shut down gracefully. That's no problem. but there might be other scenarios where it says, I'm turning you off in 3 seconds, okay, bye. And power disappears. We don't want to lose power quite like that. So we've got our UPS, which gives us the capability to slowly and gracefully power our experiments down and then power them back up again. You'll notice there's some circuit boards strapped on top, and that's currently our prototype watchdog system. So this allows us to manually restart our Raspberry Pis if we need to. If one of them gets into a lock situation, we can restart it. And also if we lose power partially, we can use this to reboot the Raspberry Pis. One of the big things that we've had to deal with throughout this entire project has been that once we say goodbye to the Mayflower on the 19th of April, we have no control over anything in it at all. We can't just pop in a dinghy, sail over and hit reboot on it. It's really got to stay going for 14 days, no matter what. And so we've tried to think about as many of the edge cases and unlikely scenarios as we can, to think around them and think of solutions to make this system work. On the top of the enclosure, you can see we've got two other boxes. One of them, which is our IMU, which is the one with the white label there. That's our IMU for our wave energy experiment. It's very, very accurate. It's the kind of IMU that you would put in a rocket or something to understand exactly where you are. So it's really interesting to try and use these different technologies on the sea. And then in the green box at the very top, that's our digital signals processor for our hydrophone. Developed by a company called Iris Aqua, who normally all of this would be packed inside a small pod about the size of a Coke bottle, and you would dangle it off the back of your ship. We didn't want to risk that, because if you have an autonomous ship with a long dangly thing behind it, there's a real risk that you could pick up some debris and you could actually just tear it off the ship or cause damage to the ship. So that's why we've mounted everything underneath, and we needed somewhere slightly different to put the signals processor. So that's all inside our enclosure as well. We've got quite a lot of passive heat dissipation in there as well. Those Raspberry Pis, whilst they're small and low powered, they do pack out a little bit of heat. So we've got some fairly big heat sinks in there to keep everything at a good temperature as well. And it's been really interesting to build this kit, because coming from a normal sort of just hack it together and see whether it works. If it doesn't work, you can just hit reboot kind of mindset in previous projects. Having to think about something that's going to go on a ship for 14 days where you can't touch it, and when it arrives at the other side, you probably can't touch it then either, because we're not going to fly to the US. It's just got to keep working. So you've really got to think about some different methods for building this kit. Underneath the hood a bit more, this is sort of a block diagram of how all of our hardware fits together. You can see that we've really tried to separate ourselves from the Mayflower itself. So we will only take power and network from the Mayflower. And the only reason we've got network really is so that we can get access to a few other sensors, but also the ship's 4 and 5G routers and the satellite comlink, so that we've got access to send data out. More or less everything in the science pod is self-sufficient. So you could imagine that, yes, we're working with the Mayflower autonomous ship here, but actually if someone had a cargo ship that they wanted to donate some space on for some science, you could quite easily take the same pod, strap it inside and put some different sensors on it, and it would work just the same. Obviously we don't have space for all of our sensors, so you can see we've got a few that are mounted outside, like our hydrophone, our GNSS receivers, which obviously have to be outside the ship and pointing at the sky, and our hypertaste array. A lot of this wouldn't be possible, obviously, without the software. So there's a fair amount of open source software that goes into this. In fact, it's all pretty much open source software. We're trying to keep this as open as possible. So our monitoring and storage of all of our stats and things is being done by some InfluxDB and some Grafana. So whilst we're doing the sea trials, we should have 4G access to it if it's relatively near the coast. So whilst it's actually running the experiments and under load, we can keep an eye on it and make sure that there's nothing in there that should cause us concern. We're also using a technology called Node-RED, which you may or may not have come across. Node-RED is a fantastic flow-based programming tool. It actually came out of the same department I work in ETS. But if you've ever played with a Raspberry Pi, you'll have actually seen Node-RED comes bundled with it. And it's a technology that lets you drag blocks onto a pallet, and you don't have to write any code at all, or you can if you want. It's powered by Node.js under the covers. And it lets you, rather than sitting in loops and waiting for things to happen, you can actually react to events as they happen. So the example you can see here on the top left is part of our monitoring solution. So we're monitoring an internal environment sensor, but we're also receiving updates for when parts of the system restart. So if something crashes and it restarts, we'll get that notification and we can log it. We'll also be using that to listen to the GPS position of the ship. So one of the aspects of this science pod is going, well, science experiments on their own might just want to collect data for the whole 14 days, but other science experiments might actually have some overarching high-level goals, and we might want to listen out for events happening around the Mayflower to maybe trigger some of those things. So for instance, we might have a GPS sort of zone set up so that we're listening as soon as we pass within a particular GPS area of some latitude and longitude. We might trigger an experiment to start taking samples. We might also, and this is really a goal for the future, we might actually feed back from the experiments all the way up to the AI captain. So, and please keep in mind, this is a sort of a very long-term goal, but if you could imagine maybe 3 Mayflowers in concert sailing across the Atlantic Ocean, all with a hydrophone on them, all listening out for whale song, and then you hear whale song, the 3 experiments could actually coordinate together and say, right, we know roughly where those whales were because we can triangulate the sound, and they might then go and ask the AI captains of their ships and say, could we please travel maybe 60 miles northeast, because we think that's the direction that these whales are going and we'd really like to follow them along. The experiments could actually ask that of the captain, and the captain could then add that into its big sort of melting pot of mission parameters and say, well, I know I roughly need to go in this direction. Is going 60 miles to the northeast going to be that much out of our way? Maybe not. And it might change the course and say, okay, then we'll go that way. But at the same time, we might have other mission parameters saying, actually, we only want to be sampling water from this particular area. So, you can't go more than 50 nautical miles in that direction. So the experiments might actually sort of fight each other for a bit of priority and trying to get their own mission goals done completely autonomously. You give them a overarching goal, you set the ships loose, and they're able to decide on things as they're on their own. Because at the end of the day, whilst it is on Earth, so we could potentially have satellite coverage of the ship, you might not always have satellite coverage. It's quite difficult to maintain a good satellite link with some of these ships. If you've ever watched footage from SpaceX when they land their Falcon 9 booster on the drone ship, it's almost a certainty that as soon as the drone ship gets near the booster, or the booster lands on the drone ship, you lose video signal because it's just being knocked around too much and they can't maintain a solid link. And that's a big issue when you're at sea in a very windy conditions. You're moving all around. So you want the ability for the experiments as well as the captain to be able to make their own decisions. Finally, and this is sort of a little bit on the side, this is another stretch goal for us, is our educational outreach. So obviously the Mayflower is a huge opportunity to trial AI captains and remote science, but also why not expand that remote science to schools? So we're in the process of working on building an educational outreach program with the Mayflower to give primary and secondary school students, primarily in the UK, but we're hoping to open it up to the whole world, the ability to write their own code and experiments for the Mayflower. So for primary school students, that might just be here's a crash course in how to write a program, and your program will run on the Mayflower. Maybe it'll take a photo with the camera and send it back to you. But for the secondary school and older students, we really want to get them thinking about ocean science, and can they design their own experiment? Given all of the sensors that we've got on the ship, if we gave them access to those sensors, could they come up with their own hypotheses and ideas for a science experiment that they could run on the Mayflower? And that's definitely our aim, is that in April, when we set sail, we can say, well, we've got the IBM research experiments, we've got Plymouth, Newcastle, Birmingham University experiments running on the Mayflower, but actually there's some really sharp kids who are from a secondary school somewhere, and their science experiments running on board as well, and they'll get their results back just as everyone else will at the end of the voyage, and they'll be able to process the results, maybe write a report up, and maybe get something out of that as well. So that's really where we're going. It's very early days with our educational outreach at the moment, but we're hoping it's going to be possible. We've got 6 months until April, so we've got plenty of time. We've just got to make it work. That's everything I have more or less for you today. I would love to tell you that if you go to the website mas400.com, mas400.com, that's where you can learn all about the Mayflower. We've got a dashboard up there that currently shows the Mayflower docked in Turnchapel Wharf in Plymouth. That's where it's currently being finished off at the moment. But during the voyage in April and during the sea trials, you'll be able to watch it bobbing around in the ocean live. We've got loads of information there about the experiments we're doing, and we're going to be putting more and more up there as the months go on and we make more and more progress with the Mayflower. So I encourage you to go out and have a look at that if you're interested. We've also got some Twitter accounts. AI Mayflower is the Twitter account for our AI captain, and Artie has 7 legs. You saw on our previous slide this cute little octopus. He's our educational outreach sort of spokes octopus, and he's going to be tweeting about the Mayflower as well, hopefully with a bit more of a child-friendly approach. Also, I'd like to thank our colleagues at all of the research organisations we've been working with, as well as MSubs, Marine AI Limited and Primare, who have been doing an absolutely fantastic job on the Mayflower. I'm really looking forward to seeing it set sail in April. I hope I've piqued your interest, and yeah, if you've got any questions, please just let me know. Over to you, Sophie.
Thank you very much, James. I found that super interesting. Does anybody have any questions? And if so, please put them in the chat, or I can unmute you if you'd rather ask it personally to James. We don't have any so far. So I had a couple. So you talked about like the SOLAS and the regulations and rules and stuff that all the boats have to abide by. How long did it take you to have to learn all of that to be able to actually implement all of this kind of thing? Because that's presumably you didn't have all that knowledge up front before this.
No, so fortunately the team who's been working on that are in IBM Edge, and the other organisation, Marine AI. Fortunately, these rules are actually written up fairly cleanly, so it's easy to understand. It's actually quite easy to convert these into machine understandable rules in ODM. I'd say it probably took more time to train the image classifier on all of the images to do that. I think it's been this whole project has been several years in the making already. I think it was first announced maybe 3 years ago. So it's been taking about 3 years to get both the image recognition and the rules-based engine really up to scratch. One thing I didn't mention actually is that at the moment we've got a manned vessel, which is floating around Plymouth Sound, where they're moving the vessel around, they're interacting with other ships, and they've got all of the same sensors and inputs that the AI captain is going to have. And they're sitting there watching it going, right, what are you doing in this situation? And it's basically saying, oh, I think I'm going to do this. And they look at the rules, and if that's right, then they're happy. If not, they have to go in and change it. So yeah, it's quite a complicated process. But I think one of the good things about it is that because it's very rules, the documentation is very rules based, it's been quite easy to convert that into a sort of a more machine understandable version.
How did this project even get started in the first place, and how did you get involved with it?
So the Mayflower project started a while ago. It was so Brett Phaneuf was he's the creator of Primare, the marine research organisation, and he lives down in Plymouth, where the Mayflower originally set sail from. And they were looking, going, oh, it's the 400th anniversary in a couple of years. We should do something about it. And a few people had some ideas, and some people said, oh, let's build a replica Mayflower, like the old wooden ship originally. And he went, nah, that's old. Why do something old? We should do something new for it. And so that was really where he thought, well, we can take marine research and this opportunity of the 400th anniversary and really merge those two together. So that's where the project really started. And then my involvement came from my colleague Rosa Licorice. She's been working really hard within IBM Research to help get a lot of IBM Research experiments on board the Mayflower. And she's the person who's working on the whale song experiment. And so she spotted that Wimbledon had been cancelled back in April this year, and she knows that that's normally what takes up most of my time during June, July, and August. So she dropped me a note and said, "Hey, now that you're not doing anything, how do you feel creating a science pod cluster for the Mayflower?" And I thought, that actually sounds pretty good. So it's been an odd set of circumstances this year, as I'm sure everyone can attest to. But being able to sort of divert all of my energies to this has been really interesting.
Very cool. You also have a question from Mike. Is there any redundancy in the mass propulsion system, for example, if the motor breaks down?
That's a really good question. I believe there is some redundancy built into the system. I can't quite say what there is, though. Unfortunately, I'm not quite a marine engineer to go through that. A lot of this, though, is focusing on the technology. It's very much a proof of concept. So whilst we might not have all of the redundancy there yet, I've been reminded multiple times I've only got one switch in my cluster, and I really should have two to have some network redundancy. It's something that we're probably looking at for a future version, but I think there is definitely some redundancy baked in. We've got power redundancy, so I think we've got some propulsion redundancy as well.
And what are the rules regarding responding to SOSs from other vessels?
Yeah, that's really interesting. So we don't have a clear view on that at the moment. Because we're an autonomous vessel, there's not really anything that we could do for another vessel. If it's a save our souls situation where there's people's lives at risk, there's not really anything the Mayflower can do. It can't support people on it. It wouldn't be able to take any extra weight. So if there was a situation like that, I don't think that the Mayflower would be able to directly intervene, but we may definitely pick up that radio transmission. And if that happened, then we're always getting a feed of those back to us, so we might be able to pass it on. I think that's probably where we would end up. We are looking at obviously, a lot of ships' captains communicate with each other over a VHF radio, and the AI captain doesn't yet have a voice. We are working, though, on it's a fairly difficult research problem of decoding human speech over radio. The moment you use something like VHF radio, voice recognition almost entirely goes out of the window. So trying to build better voice recognition models for VHF radio is something we're definitely looking at, because at the very least, we would like the Mayflower to be able to listen to calls from other captains, maybe saying, "I need you to get out of my way. I can't." Maybe the other ship has a propulsion or steering issue, and they're saying, "Look, you need to get out of the way," and they can't signal that any other way. The Mayflower should hopefully be able to understand that and follow those instructions. So yeah, we're definitely looking at being able to receive audio transmissions, but it is quite a tricky research problem that we're working on.
That was a really good question. I haven't thought of that. Cool. I think that's it then. I mean, my only other question was, when do we get to hear your sea shanty?
Well, not from me specifically, but if all goes well, we should be able to listen to it at least during the voyage itself, if we're very lucky. Otherwise, we'll probably have a full captain's log that the AI captain will write for itself, which will include the sea shanty once the voyage completes, which will be probably around the 28th or 30th of April next year. So watch out for that.
Very cool. And can we subscribe for updates?
Yes, definitely. If you subscribe to the AI Mayflower Twitter account, you'll hear all kinds of updates there. We've also got some YouTube documentaries that are coming out. The first one's already been released. It's called The Uncharted. The next episode is starting filming around now, and that's following the design, conception, and sort of building of the Mayflower. So that's on the IBM YouTube channel.
Cool. Thank you very much.
Everything you need will be at mas400.com.
Cool. Thank you. Cool. I think we'll end it there then. Thank you very much. I found that really interesting. I hope other people did as well. And if everybody can please go and give James feedback on his presentation as well. So if you go back to the GSE website under the build your own agenda bit, there'll be a link in there for you to, oh yeah, and there's your link as well. So this was session 5AB. So please do your feedback. So thank you, everybody.
Yeah, thank you very much, everyone.